We have discussed the idea of chemical bonding and focused in on the covalent bonding specifically. We mentioned the idea of a Lewis dot structure, so now we need to begin to draw Lewis dot structures. The first molecule that we're going to attempt to draw is ammonia. The formula for ammonia is NH3. The first decision that has to be made whenever you're going to draw a dot structure is to determine what the central atom should be. Now, the central atom will never be hydrogen. Hydrogen comes with only one valence electron, so therefore it will only bond one time. That makes it very difficult to put it in the center of an atom. If there is a choice as to a central atom, usually the central atom is the atom that is the least electronegative, or another way to look at it is the element that typically will bond the greatest number of times. So it will have the greatest number of single dots around it when you place the valence electrons around the central atom there. So in this particular case, then nitrogen is the central atom. Now, once you've decided on a central atom, then you need to determine the total number of valence electrons in the structure. Now, nitrogen, as we said before, is in group 5, so therefore it will have 5 valence electrons, and hydrogen is in group 1, so it will have 1 valence electron, and when you add the 3 hydrogen valence electrons to the 5 valence electrons on nitrogen, we end up with a total of 8 electrons that we need to place in the structure. Now, once you have the correct number of valence electrons and you've decided on the central atom, you want to draw that central atom and form a single bond between the central atom and each of the surrounding atoms, at least a single bond. We may at some point add double bonds and triple bonds, but you at least want a single bond to the central atom attached to the other atoms surrounding it. The remaining electrons then, if there are any, go on the central atom to complete the octet, or they may end up on those elements surrounding the center atom. But the idea is to make sure that there are 8 electrons around every single element in the structure, with the exception of hydrogen. Hydrogen will only have 2 when it is bonded. Now, once you have the structure drawn, you need to check to make sure there are 8 electrons around each atom except for hydrogen, and then you also want to make sure that you have not exceeded the total number of valence electrons. Now, we said that the total number in this particular structure should be 8, and if we look at the structure of NH3 there and we count each bond as a pair, and then we count the lone pair, there are a total number of 8 electrons. So the structure that you see there is the structure for NH3. Now, what happens when we get to a slightly different molecule, such as carbon dioxide? Again, we want to identify the central atom. So we have our choice between carbon and oxygen. Carbon happens to be the least electronegative element of the two, so we're going to place carbon in the center. And then we also want to determine the total number of valence electrons. Now, oxygen comes with 6, and there are 2 oxygens in the CO2 molecule. And oxygen together with carbon has a total of 4 valence electrons. So we add the 4 valence electrons from carbon and the 12 valence electrons from oxygen, and we should get a total of 16 valence electrons. Now, just as in NH3, we want the central atom drawn, and then we want a single bond to at least the 2 other elements. So we're going to place carbon in the center there, and then place oxygens on either side with a single bond. Now, we've only used really 4 electrons, so that means we still have 12 electrons to place in there somewhere. So our next step here is to place all the lone electrons on the outer atoms, and then we want to make sure that all atoms have a total of 8 electrons. And as we look at this structure, we can see that the oxygen on the left has a total of 8, the carbon in the center a total of 8, and the oxygen on the right a total of 8. We count those bonded pairs of electrons for both of the elements. So the carbon in the center there, the bond to the oxygen on the right, that bond counts as a pair for the carbon, and it also counts as a pair of electrons for the oxygen. Now we need to then determine whether we have our 16 electrons, and as we look at the drawing here and count up the number of electrons, if we count up the number of dots and we count up the number of bonds, we actually end up with more electrons than we really should have in the structure. So if you look at the structure there's 2, 4, 6, 8, 10, 12, 14, 16, 18. There appear to be 20 electrons in the structure. Now when that happens, when there's too many electrons, what we can actually do is take a pair of electrons away and then create double bonds. So as you can see down there at the bottom of the screen, we've removed a pair of electrons from the top of carbon and a pair of electrons from the bottom of carbon. So we've taken away those 4 extra electrons. And now what we're going to do is pull electrons over from the oxygen and then bond to those electrons. So as you can see in the second drawing here, the red bond at the top there, the top part of the double bond, that's actually a bond that's formed when we move an electron from the oxygen over there to the carbon, and we've created two double bonds on either side of the carbon there. Now if we count up the total number of electrons, you'll see that there are actually a total of 16 valence electrons, which is what we actually want for the CO2 molecule. So anytime we create single bonds, put in 8 electrons around every single element in the structure, and then find that there's too many dots, the next step should be to begin to remove electrons and to start to create either double or triple bonds. Now, typically, elements which participate in double bonding and triple bonding would be elements such as carbon, nitrogen, phosphorus, oxygen, and sulfur. Now there are more than just these elements, but these are your pretty typical elements participating in double and triple bonds. Now, there are some exceptions, of course, to anything, and there are exceptions to the octet rule. That is, there are elements that when they bond, they typically will not have a total of 8 electrons around them. And we've listed here several of those elements. So beryllium, typically, when it bonds, a total of 4 electrons around. Boron, a total of 6. Now, phosphorus, sulfur, and xenon can exceed the octet rule. So typically they'll have 8 electrons around when they're bonded, but phosphorus may go up to 10, sulfur may go up to 10 or 12, and xenon can go up to 10 or 12. So these last 5 elements here can violate the octet rule.